Okay, guys, as fate would have it, the computer decided to crash. Lost my R, lost everything, but I was able to save a little bit of the video. Uh, so we're starting off where we kind of ended up. Since R crashed, let me show you what I've done here. I've gone into R and just gone ahead and set everything up to get us back to where we were before. If I remember correctly, we were at the end of the video that previously I had just created the diagonals of the hat matrix, which we need. And again, the goals are the same. We want to create this data frame that includes the residuals, our HIIs, and our standardized residuals. Okay, so let's get that going. I think it looks like I've got everything set up to where we can make this happen. The next thing that I'm going to need is I'm going to need my residuals, and just like I did before, I'm going to call those RESID. No, I'm not. I'm going to shake it up a little bit. I'm going to just call those RES. And our residuals, remember, we can get those a couple of different ways. We can take the observed minus the predicted. And of course, did I create beta? Yeah, I did. One of the easiest ways to do that is just take x times beta. So, guys, again, I wanted to create the errors, which I've done now. I wanted to create the h sub i's, which I've done. So now I need to create my standardized residuals. Okay. Now, what I would like to do is to go back over to the to this. I don't even know what I really call that thing. To go back over here to this, and let's create the standardized residual for the first observation. Now, guys, remember that's going to require us to do the error for the first observation, and we're going to use the process where we don't have to create two models or an additional model. So I'm going to need n minus k minus 2, which I'll always need to do. I need to create the sum of squares for the error. I don't think I've done that yet. And then I need to take, let's get that out a little bit, minus e sub 1 squared. Okay, so I need to do that for the first observation. So we can see that I need a couple things. First thing I need is the residual for the first observation. I need n minus k minus 2, which is pretty clear. And I need the sum of squares error, and I need h11. So if I can get all that, I'm going to be in pretty good shape to calculate the standardized residual for the first observation. So we can go over here and we can clearly get that information. So I can just go residual and get the observation, the residual for the first observation. So I'm going to call that, I'm going to go out 3 places on this. I'm going to call that negative 2.955. Now the next thing I needed was n minus k minus 2. So I have a sample size of 20. I have 3 predictors. Minus 2 gives me a degree of freedom of 15. Guys, next thing I'm going to need is the sum of squares error. So I'm going to call that SSE because I'm really creative like that. And all I need here is the sum of the residual squared. Oh, I changed that, didn't I? All right, so gang, sum of squares error is going to be 98.405. And the next thing I need is I need my HIIs. So the H11 would be 0.341. And again, this would be, if I just looked at that hat matrix, that's going to be the diagonal for row 1, column 1. All right, so let's get back over here, and I need to grab my calculator. So what are we going to have here? We're going to have the error is negative 2.955 over the square root of 15 divided by the sum of squares error is 98.405. 1 minus, so it's going to be 1 minus 0.341. And this is minus 2.955 quantity squared. All right, guys, grab your calculator. I'm going to grab mine. So I'm going to take care of the denominator here. I'm doing this only because if I make a mistake that you guys can help me out. So I have 98.405 times 0.659, and that will be minus 2.955 squared. So it looks like in the denominator we get 56.117. All right, so I'm going to nick negative 2.955. I wish I could show this on the calculator, but I think you guys can handle this. So if I don't have any typos at all, I get a standardized residual of negative 5.528. Okay? Now, what I'd like to do now, again, keeping as my end goal is, remember way back when, before all the computers, and actually I got interrupted by the neighbors too. You guys didn't see that video. Got about 10 minutes in and the doorbell rang, so started over because it was only 10 minutes in. But guys, nevertheless, what we want to do is we want to create that final column of our standardized residuals. So let's go back to R and let's make that happen. So guys, what I'm going to do now is I'm going to take the standardized residuals. I'm going to create a new vector of standardized residuals. And I'm really just going to repeat what I did before with some calculations. Now, I'm going to cheat a little bit here, and I'm going to do DEN1. I'm going to do some calculations for that denominator before anything else. So the denominator in the square root. So guys, the denominator in the square root is going to be our sum of squares error, which I keep forgetting for some reason, 98.405. And I need to multiply that by 1 minus my HIIs. And I want to make sure there's no misunderstandings with R here. And then I want to subtract my residuals squared. Okay, so guys, I think we're ready to just do the standardized residuals here. So I want my residuals times square root of 15 divided by the denominator 1, as I just called it. So I've got my standardized residuals, and if we did everything correctly, which I'm pretty sure that we would, notice that our standardized residual for the first observation turns out to be negative 1.528, which we would hope. So guys, I'm going to call this new data now, and I'm going to do a data frame. So I'd like to step back and just, again, take a look at what I need here. So I want body fat. And I'll tell you what, it's really going to help me if I do this. Okay, sorry about that. All right, so I want my Y, which is body fat, first. And then I want my X1, which is triceps. And then I want thigh, and then I want mid-arm. And the next thing I wanted were my residuals, my errors. The next thing I wanted were the diagonals on the hat matrix. And the next thing I wanted were the standardized residuals. All right, gang, this is going to give us what we set out to create. So what I'm looking at now to illustrate carrying out this test, all right, what I'm looking at now is the highest standardized residual. Now, one thing you can do, I mean, we've only got a data set of 20 here, which is completely and totally manageable. But what you could do, let's say you had 400, and you start eyeballing this, and you start losing your mind there. What you can do is you can sort your standardized residuals, and you can look at the extremes. So we have one at negative 1.71, and then the highest is at 2.01. So guys, our focus, I'm going to write this down. So that's going to be the 2.01 is going to be on the 14th person. Now, okay. Well, I kind of noticed something kind of interesting here. I don't know about you guys. Yeah, I think I'm going to leave that one for academic exercise, okay? So the 14th person here has a standardized residual equal to 2.016. Okay? Now, what we're going to do next is we're just going to carry out a test to see if this is statistically significant. And we want to use a Bonferroni correction. So what typically a Bonferroni correction does is it takes our alpha level. Now, we know that our degrees of freedom, and I'm going to write this over here, we know our degrees of freedom is 20 minus k predictors, which was 3 minus 2. So we're dealing with the t-distribution degrees of freedom equal to 15. So, so the underlying probability distribution here is t degrees of freedom 15. And if alpha is equal to 0.05, then if we're conducting a two-tailed test, we would need to come up with our t critical values for this. Okay, so let's go do that. That's going to be really easy to do. So we just do QT 0.025, degrees of freedom 15, and we see that it's negative 2.131. And of course, positive 2.131. So we can calculate the p-value pretty straight up here. Okay. So let's go ahead and do that. So I want the area, we have a positive 2.016. So I want to go, what? I want the area in the upper tail, so I need to go 1 minus PT of 2.016 degrees of freedom 15. Now I need to multiply that by 3, so my p-value turns out to be approximately 0.06. So, you know, there doesn't appear to be statistical significance here because using the Bonferroni correction, and let me illustrate that to you. The Bonferroni, the alpha adjustment typically kind of works this way, and this is all about controlling the type 1 error rate over multiple comparisons. Okay, and one thing that you can do here is you can take your alpha and divide by the number of hypotheses. So we have an alpha of 0.05 if we're testing 20 cases, 20 deleted residuals. We could take 0.05 divided by 20 and test at 0.025. So we would not reject unless we got a p-value less than 0.0025. Now, the Bonferroni correction that I talked about earlier is to take the t of 1 minus alpha over 2n at our degrees of freedom n minus k minus 2. Let me show you what I meant by this. So we can take t 1 minus if we're testing a 0.05 and divide by 40 instead of 20 because this is much more conservative Bonferroni correction method. And again, we'd have degrees of freedom 15. So ultimately, guys, what we get here is we get t of 0.05 divided by 40. And take that away from 1. So we get 0.99875. Now, essentially what this is saying is that the area between the two cutoffs needs to be 99.875%. So we can subtract that from 100. And divide by 2. And we get 0.0625 and 0.0625 in this tail. All right? So what we need to do is we need to create our critical values here. And let's just let's do that. So this is using the Bonferroni correction that you see quite a bit presented for this process. So what I need to do here, I want QT and I want 0.0625 in the left tail with degrees of freedom 15. So I have negative 1.625 and positive 1.625. Guys, that doesn't seem right. Let me, I think I'm, yeah, oh shoot, I made the freshman mistake. Oh, that's embarrassing. I don't care. I had, so this should be 0.99875 minus 1. And then divide that by 2, I get, wow, that's embarrassing. Oh well. 0.000625 in the left-hand tail. I was going to say that didn't mesh up, did it? So let's do this correctly this time. Well, let's not us do this correctly. Let's let your bozo professor do this correctly. So guys, that's much more appropriate. You know what? I'm tempted to redo the video just because of that, but I'm not. I want everyone to see that I'm human and I have moments. And that was actually definitely a moment. So 3.963 and plus 3.963. And our test statistic that we calculated, or our standardized residual, was 2.01. So we can go back over here and see that 2.01 would fall in our fail to reject region. So there's no reason to delete that case because its effect on our model isn't statistically significant. So deleting that really doesn't change things statistically. Okay, guys, that's all I got. So on your homework assignment, I want you to use this approach. This would be a good way to figure out whether you're watching all the videos or not. If you start doing something wacky on me, I'll know that you didn't finish it up. So guys, use this approach in your homework assignment. Any misunderstandings? All right, use this approach. Gang, that's all I got. Take care.